Hi guys, so today the attempt is to go over a simple chapter that's called Areas Related to Circles. Learn a few basic concepts which I think we've already covered in the previous classes or at the beginning of the year. But the goal here is to relook at those concepts, the formulae, and immediately apply those on a quiz. Okay, so please have your notes, a pen and paper ready. Make a note of all that you have forgotten or something that you've learned newly as part of this session, and then attempt the quiz. And the goal of the quiz is to get your answers right. So please focus on accuracy, and then you can worry about speed. Okay, cool. So here we go. The agenda is, we will look at area and circumference of a circle, right, which is what you've been studying from grade 7, I think. And then we will extend that to learn about the length of the arc of the circle and look at how do we calculate the length of minor and major arc, okay? And then we look at the perimeter of a sector, the area of a sector, and definitely the area of a segment also. Cool. And then we'll apply these on certain sums. Okay, the sums could be direct application problems, or we could apply these on scenarios of a wheel rotating and hence covering a certain distance, or it could be the hands of a clock, so on and so forth. And last but not the least, which gets very interesting, is that of the combined figures, okay, where you could have a shape within a shape, okay, you could have parts of a shape, let's say parts of a circle that is shaded in a rectangle. You could have arcs cut like these, and then you would be asked to find the shaded area. Or it could be a couple of shapes superimposed on one another, okay, something like this, right? There could be various of these, and I think working on the combination of 2D figures and finding the areas is very interesting. So let's look at those. We're going to break this up into 3 parts. Okay, part 1 is just the basic: circumference, the area of a circle, arc length, area of a sector, and perimeter of a sector. These are very intuitive, so let's look at part 1. So folks, if you have to define a circle, right, usually, you guys fall back to defining a circle as a curve, a shape with a 2D shape with no edges, with no sides, and all of those, right? But a new way to look at a circle is to define it as a locus of points, okay? I've used a new terminology, locus, here. We'll get into it in a bit. A locus of points on a plane or a surface that are at a certain distance from a central point or a fixed point. You can call it any way you want, okay? But what does this mean? When we talk about locus, a locus is just a shape or a figure that is formed by points satisfying a certain condition or a rule, okay? In this case, what is that rule? The rule says that if I fix a point, okay, and from this fixed point, I cover equal distances at a fixed distance, I keep traversing this path, then I end up with a circle, okay? So a locus is a shape formed by all those points that satisfy a given condition. And for a circle, that condition happens to be that from a fixed point, which we call the center, we look at all those collection of points that are from a fixed distance from the center. And this fixed distance we know is the radius, and the fixed point is the center. Okay, so we can actually define a lot of the 2D shapes using the concept of a locus, right? When you study about quadratic equations, I think you know that the curve you get when you plot a quadratic equation is a parabola, right guys? I hope you remember that. So if a parabola is like this, then what's unique about the parabola is that if you have an axis of symmetry, which for in this case happens to be the y-axis, then all the collection of those points that are at equal distances from this axis of symmetry, okay, gives you the parabola. So locus is a way of defining the shape. Cool? I hope you got it. And then definitely, before we even look at the formula for circumference or area, it's very important to understand what is pi, right? When we talk about pi, people usually say, oh yeah, pi is 22 by 7, pi is 3.14, but that's not what we are interested in. It's not the numerical value. The significance of pi is that it is a constant, and that constant is the ratio of the circumference of a circle, okay, to its diameter. Right, guys? So this is a fixed ratio, and the number is always the same. It's a constant, and that is the beauty of pi. It's from here that you get the circumference of a circle to be pi into d, or d is the diameter, or it is actually pi into 2r, or the circumference is 2 pi r. So the circumference is obtained from pi. An area of the circle, we've looked at a video also last time that it is pi r square, how we actually break the circle into smaller pieces, and when you lay them out, it kind of, stacks to form a rectangle. The link to that video will be in Google Classroom. But nonetheless, these are the things that you're very familiar with from grade 8 onwards. Okay, this is just a recap. Moving on. So in grade 10, you'll extend the concept of polygons that you've already studied, any closed shape with 3 or more sides, and a lot of properties that you studied about polygons. And then you've also studied a lot about circles, right? Properties of circles, tangents, area, circumference, all of that. And then you put these together and learn more about calculating the perimeter shape, the area or the shaded area of inscribed and circumscribed polygons. What do we mean by this? It's pretty straightforward. An inscribed polygon, as the name suggests, is a polygon in which all vertices lie on a circle. So in figure A out here, we have a polygon which is a triangle ABC that sits inside a circle because all the vertices of this triangle are on the circumference of the circle. So you say that a triangle is inscribed in a polygon. A triangle is inscribed in a circle. Okay, so in this case, the triangle ABC is the inscribed polygon. Okay, and in figure B, we have a quadrilateral ABCD that's inscribed in a circle. And in figure C, do you want to guess what sort of polygon this is? How many sides it has? How many does it have? 7, right? So it is a 7-sided polygon that is inscribed in a circle. Okay, it's not necessary for these polygons to be regular polygons. Okay, it's just that as long as I can have the vertices of a polygon lie on the circumference of a circle, it's an inscribed polygon. Well, you also studied in the previous chapter that this polygon has a special name. Do you remember that? It's called a cyclic quad, right? Cyclic quadrilateral, and you learned certain properties about this. Okay, moving on. we have what is also a circumscribed polygon. What does that mean? It is a polygon that actually has a circle sitting inside it, okay? And by virtue of that, what's happening here? So if I name this polygon PQRS, oops, yeah, PQRS, you'll observe that each side of this polygon happens to be a tangent to the circle, right? So if you look at PQ, PQ is a tangent, QR is a tangent, SR is a tangent, and so is PS. And from here, you can actually look at a lot of the properties you learned as part of the tangents chapter, right? The tangents drawn from an external point are equal. So if I were to name this point as C, right? PC is equal to PD, QC is equal to QE, so on and so forth. So what you'll see in this chapter is you kind of, it does not matter what the question is, but you should be able to link all those concepts that you've learned about polygons and circles and the information about the area, perimeter, and so on, and try to look at a combined shape. Okay, fantastic. So there's one more thing that's new out here. That is, when we look at circles that not the circles that intersect one another, but that might just touch each other at one point. In this case, there are circles that touch each other internally. There's one circle that is inside another. Okay, so if O happens to be the center of the larger circle, center, and O dash happens to be, right? Let's say O dash is the center of the smaller circle. I'll mention that here. Okay, I'm constantly looking at whether the session is being recorded. Otherwise, I'll be talking to myself and see that the record button is not on. Okay, it's recording. So the circles touch each other internally. O is the center of the larger circle. O dash is the center of the smaller circle. Okay. In this case, what we are interested to find out is what is this distance between their centers, right, guys? If I asked you what is O dash, or O dash is actually the distance between the centers, and that is equal to the sorry, I didn't mean to write O. It is the measure of the radius of the larger circle minus the radius of the smaller circle, right? So if this is the radius of the larger circle and this is the radius of the smaller circle, when we subtract that, we get the distance between their centers, right? Very easy. The same thing if we have to extend to circles that touch each other externally, how would that look? So we have O being the larger circle, O dash is the center of the smaller circle. In this case, okay, the distance between their centers, oops, is nothing but O dash is the radius of the larger circle plus the radius of the smaller circle. Okay, remember this fact because in the quiz you will have to arrive at certain missing attributes of the circle if the areas of such circles are given. Okay, cool. As and when needed, please pause the video, make a note so you have all the formulae in one place. Right, guys? Okay. Moving on. Let's correlate the circumference of a circle and the arc length of a circle. Okay. So here's a circle, and we all know that the circumference is 2 pi r. Okay. Then we have another circle. We've broken it down into two parts, two equal parts. So the one in red is the semicircle, right, guys? So in this case, if I talk about arc AB, In this case, arc AB, you can't distinguish whether it's a major or minor arc simply because whichever way you measure the arc, the length is the same. The major and minor arc are equal in length, which means we've split the circle into two parts. So here, as you can see, if the arc length, I'll write the word arc length here. Okay, the arc length of AB is 2 pi r by 2 because you're splitting it, the entire circumference into two parts. So it is pi r, or if you think in terms of the angle subtended by this arc at the center, which happens to be 180 degree because AB is a diameter and diameter is a straight line, then you can say that the arc length is also, right, if the way you can look at pi r is 180 degrees over 360 degrees, right? We've done this before because the angle around a point is 360. So it's 180 by 360. It's a slice of the circumference, right? So even in this case, you will get a 1 over 2 and the 2 cancel each other out and you get pi r. Okay, so you can look at it in both ways. And then we have an arc that is obtained by forming a quadrant. You have circle with center O, you have arc AB in case 3. In this case, it is a quadrant, which means it's 1/4 of a circle. Therefore, the arc length, so here is what I'm writing. The arc length for this is, you have a circumference 2 pi r, you split it into 4 equal parts, or I find 1/4 of the circumference, which will give me pi r by 2. Another way of looking at it is, you have an arc AB and the angle subtended by the arc at the center. We've studied about this in circle theorems. Angle subtended by an arc at the center. What is this called, guys? This is called the central angle. Right? Apologies for writing it in different places. But for a quadrant, the central angle is 90 degrees. So it's 90 by 360 into 2 pi r. It's a slice. It's a slice of the entire circumference. So here you get 1 by 4, or you cancel this, you get 1 by 2. So it's pi r by 2. So if you extend this thought process, and I have any arc, okay, O is the center, PQ is an arc, as long as I know the central angle theta, then I can say that the arc length is a slice of theta by 360 is, okay, it's a part of the entire circumference, and that part is given by theta by 360 into 2 pi r. So this is the formulae for arc length, okay? As long as you know the central angle, you can find the arc length. Okay, guys? Fine. Moving on. What is a sector? I think we've discussed this before. A sector is an area bound. The area bound between an arc and its corresponding radii. Right? Because the minute you have an arc, guys, you have two endpoints. Okay, I'm using this circle to mark those. And the endpoints are, let's say, P and Q. Then when you join P and Q, they form the radii. It is this complete area, this pizza slice, which is called a sector. It's the area bound between an arc and its corresponding radii. It's not some other radii that I can form with the point anywhere else. It has to be the radii that is formed by connecting the endpoints of the arc with the center. Okay? If you've forgotten the definition, pause the video and make a note of it. Cool. Let's look at the perimeter of a sector. Now, as usual, I have a semicircle, and then let's look at this sector AB. Okay, what we're talking about here is this, all this dotted portion is the sector. Now, when we talk about the perimeter of the sector is arc length AB plus, you see that OA and OB are radii, right? You add 2r to it. So always the perimeter of a sector is equal to the arc length L. We are introducing a new nomenclature or letter, arc length L, and add 2 times the radius to it, you'll get the complete perimeter. Right, guys? Now, what happens in the case of this sector, which is formed by the semicircle? You already know the arc length is 2 pi r by 2, because you're splitting it into half, pi r plus 2r, correct? So r is common, you get pi plus 2. You don't have to remember this formula, it's very intuitive. So you just have to remember to add the diameter or 2 times the radii. Same thing for a quadrant. Again, it's the arc length. We know the arc length is 2 pi r by 4 or pi r by 2, the arc length of a quadrant. And to this pi r by 2, you ought to add the radii, 2 times the radii. Why? Because you're adding this and this and then this. That gives the complete perimeter. Cool. And finally, if you're asked to find the perimeter of this sector, let me call this EF, okay? Sector OFE or EF, then if theta is the central angle, then the arc length is theta by 360 into 2 pi r, right? Plus 2r. Okay, it's the same thing. Well, you can take 2r common out. You will get theta by 360 into pi plus 1. All this is immaterial as long as you know that you have to follow this logic. Clear, guys? Okay. Fantastic. So always in the quiz also, please read the question carefully, look at whether arc length is asked, perimeter is asked, radii is asked, okay? Check what is asked and apply the numbers correctly. Moving on. How is the area of a sector related to the area of a circle? Okay, pretty easy. We have, just as a sector or an arc, just as an arc is a slice of the circumference, right? A sector is a slice of the area of the complete circle. We just have to find what proportion or what part of the area of a circle it is, correct? Okay, so we have a semicircle, we repeat the same thing. We know that the area of a circle is pi r squared. The area of this sector, which is a semicircle, right? The area of a semicircle is also a sector, is pi r squared by 2. Or as I told you before, it's 180 by 360. It is this portion or this slice of the entire area of a circle, correct? That's how you get pi r squared by 2. Let's apply the same thing to a quadrant. It is pi r squared by 4, or the angle subtended by this arc of a quadrant is 90 by 360 into pi r squared. Either ways, you will get pi r squared by 4. And then for this sector, the area of this sector PQ, if the central angle is theta, then the area of this sector is theta by 360 into pi r squared. Right, guys? Very easy. If you know the central angle, you can always find the arc length and the area of the sector formed by the arc. Okay, nothing to remember. It's very, very straightforward. Okay, moving on. Supposing the central angle is not given, okay, but instead the arc length is given, and then you are expected to find the area of the arcs. Shall we find out what that is? Okay, let's say PQ is an arc, okay, and the length of arc PQ, length of the arc PQ is L, and we also know the radius of the circle, which is R. If these two are given, is there a way to find the area? Cool. Okay. Guys, what is L? We already know that L is nothing but theta by 360 into 2 pi r. Cool. And the area of this sector PQ, in this case it happens to be a minor sector, is it not? If I worry about the minor arc PQ, this dotted area, the shaded area, is that of a minor sector. Minor sector. What is this area? It's going to be theta by 360, right? Of course, theta is not given, but let's find a relationship. Theta by 360 into pi r squared. R is given, right? Now look at these two equations. I will rewrite the area as theta by 360, okay, into, I know that there is no 2 here, but I am just multiplying and dividing by 2, no harm, right guys? Which is a 1, I'll leave it as is. And I will write this as pi r into r. I've just split the r squared as r into r. That is all I'm doing. There's no other change in this. But by doing this, the beauty is I'm going to take this 1 by 2 out. I will leave it as theta by 360, okay, it's a multiplication here, theta by 360 into, you see I have 2 pi r into r, right guys? Now what is that which I've put in brackets? Let me circle it quickly. Okay, if you observe this, theta by 360 into 2 pi r is nothing but your arc length, right? Right, guys? So can I rewrite the area of a sector as half, because I have this half taken out here, half, into L, which is the arc length, into R. So if the central angle is not given, no issues. If I know the length of the arc L, I know the radius of the circle R, then all you need to do to find the area of a sector is LR by 2. Okay, this is something you need to remember, because it's very, very easy to arrive at the area of the sector if the radius and arc length is given. Okay, pause and make a note of the same. Cool. One last thing that I have to mention here is, so finally we know that the area of minor segment, in this case it's minor segment, sorry, not segment, minor sector PQ, okay, is LR by 2. Supposing the area of the major segment is asked, for the same diagram, if the area of the corresponding major segment is asked, which is this time I have shaded this portion because this is the major segment, as you can see. If this area is asked, what are you going to do, guys? You will just, you know the radius of the circle, so obviously it is pi r squared, which is the radius of the which is area of the entire circle, minus the area of the minor sector, which is LR by 2, right? So as long as you know one, you can find the other, and the same applies to arc lengths also. If you know the arc length of a minor arc, which is either in terms of the central angle theta by 360 into 2 pi r, or just arc length L, whichever be it. The major arc is given by what? You know r, so it is the circumference 2 pi r minus the minor arc, right? Or it is 2 pi r minus length of the minor arc. So again, in questions, be mindful of whether you're asked to find the length of the minor arc or major arc, and whether you're asked to find the area of the minor sector or major sector. Okay, and you can also, if you want to, just make the questions a bit more trickier, you could also be asked the perimeter of a minor sector or the perimeter of the major sector. Right, guys? I think, let me just trace back the perimeter of a sector. Yeah, here we are. All along when I was deriving this and showing you what the formula is, we are talking about, at least in this case, for option C and option D, these are minor perimeter of the minor sector. If you're asked to find the perimeter of the major sector, just find the length of the major arc and add plus 2r, or add the radii to that. Clear? Okay. So you've learned quite a bit now. I think it's time to apply all of these because they're very easy. So look at the video once again, or those parts that needed some time. And after that, open the quiz in Google Classroom, and the quiz will be related to area, circumference, inscribed, circumscribed polygons and their corresponding area. There will be questions on what's the relationship of circles that touch each other internally or externally. And last but not the least, arc length, perimeter, and area of a sector. Okay, good luck. Do well.